Y'all ready for math? All right, folks, here we go. Our first calculus video. Okay, well, second calculus video. If you watched the last one, I hope that you did. We're going to talk today about the last chapter we have to do before the advanced placement exam. AP put out some information about your advanced placement exam. They're going to cut off a chapter. Unfortunately, the chapter that they cut off is all stuff that we already did, but that's good news, okay? Because, this thing is going to be over eventually, and you guys are going to have to, be in college. You're going to be taking Calc 2, some of your engineering majors. So I'm glad that we got through that material because I wouldn't want to just skip it, okay? We got one more chapter left, and then we could jump into AP review. We should be fine on days. The AP is going to release more information April 3rd as far as what your AP exam is going to be like, so we won't be discussing that today. Today, if you take a look at your dittos, okay, hopefully you printed them out. If you don't have a printer, by the way, you could always just look at them on your phone in PDF format, okay, and write down the problems. I know that's annoying, but that might be the way you have to go if you don't have a printer. And let's talk about solving differential equations, okay? That's what we're going to talk about today. This is technically chapter 6, okay? So there's not really room on this ditto, but if you want to, kind of crush it in there somewhere, this is chapter 6 right here, and this is differential equations. Differential equations. And slope fields. And we'll talk about slope fields, I believe, on day 3, okay? So today we're just really focused on solving differential equations. And if you take a look at this ditto, okay, a differential equation, it's just an equation that has a derivative in it, okay? You can see we have dy over dx is equal to x. X here is a function of x. Sometimes a derivative is a function of x. That's the ones that we're really used to dealing with. Look at example 2 right here. You can see that now the derivative is actually a function of y. That happens as well. Sometimes to get the slope of a function, it only depends what y coordinate you're at. That would be a situation where the function passes the horizontal line test. So that would be a function of y right there. And the third one, you could see that the derivative is a function of x and y. So you can see Mr. Matina's handwriting over here. Okay, there are 3 different things as far as the derivative is concerned. They could be equal to a function of x, a function of y, or a function of x and y. You see this a lot with implicit differentiation. We've done lots of problems where we've taken a derivative and ended up with something like this, usually something a lot nastier than that. So we'll talk about that more in AP review. So let's talk about solving a differential equation. You always want to isolate the dy over dx. I've never really seen an AP problem where it's not isolated. They could have said dy over dx minus x equals 0 here. Then you could add dx to both sides. I don't think you'll have to worry so much about something like that, but we'll talk about it when we need to. And the deal with solving differential equations, it's written right here. Good old Mr. Matina, separate and integrate, okay? That's what we're going to do. People are like, separate? What the heck is that? Separation of variables, okay? Obviously, if we start with a derivative and we want to get back to what y is equal to, if we start with dy over dx, we want to integrate. We want to go backward, okay? And the problem is, when you integrate, you have to integrate either with respect to y or with respect to x. So we have to separate the variables. You got to get the dy on one side of the equation and the dx on the other side of the equation. And these can get really filthy, but if you follow my tips and tricks, I like to call this Mr. Berto's, tips and tricks, an online strategy guide for solving differential equations. Now it's quite literally an online strategy guide. Anyway, so you'll get used to these. There are many different ways to solve them, okay? But we're going to kind of focus on a specific way. So the separate part, first thing you want to do is you actually want to cross multiply, okay? And the first part of Mr. Berto's tips and tricks, always put the dy on the left-hand side, okay? So when we cross multiply here, dy times 1 is just dy. Remember, dy just represents a number, right? Delta y, the difference of the y values. And dx times x, we're going to write as x dx. And you can see now that we cross multiplied, we're actually separated. Separating the variables just means you want x's on the side with the dx and you want y's on the side with the dy. There are no y's here, so you don't have to worry about that so much, but always put the dy on the left-hand side, and sometimes after you cross multiply, you have to move variables around. You're not separated yet, but now we are separated, okay? So after you separate, you integrate, okay? So we're actually going to integrate both sides. In the integral of dy, remember, there's really a 1 right here, right? So the integral of 1 with respect to y, that's somebody's derivative in there. Whose derivative? The answer's derivative. So you take the derivative of y with respect to y to get 1 back. But don't forget about that plus c. which I'm actually going to say is c sub 1 over here, because another c is going to be generated on the other side. You'll see after this problem, you don't have to worry about generating a c on both sides. We'll talk about that in a minute. But if you actually integrate the right-hand side, integrate x to the first, we get x squared over 2, plus another constant, not necessarily the same one, so I'll call it c sub 2. And now we usually want to end up solving for y, okay? And the deal with solving for y over here is that you do want to add or subtract this constant c sub 1 from both sides. We don't know if it's positive, we don't know if it's negative, so you don't know if you want to add it to both sides or subtract it from both sides. But the idea is that if you do subtract it from both sides, c sub 2 minus c sub 1 is just going to be another c. It's just going to be another constant, okay? Even if c is going to be a negative c sub 1, you'd add it to both sides. C sub 2 plus c sub 1 would just be another c. It'd just be another constant. So we say y is equal to x squared over 2 plus c, okay? And thus we've actually solved for y. And that's the solution to our differential equation. In the future, you're not going to have to worry about putting a plus c on the left-hand side because you're always going to be able to move it to the other side and combine it with the other c. So we're only going to worry about putting c on the right-hand side. So remember, always put dy on the left-hand side, and then just worry about putting your c on the right-hand side. And the problem is, I don't know exactly what y is equal to over here, okay? So this is actually known, because I don't know what c is equal to yet. They didn't give me any information to solve for c, like an anish can dish. And this thing right here is known as a general solution. General solution. So if you see him on the street, you should salute him, sir, because he's a general. All right, that was horrible. General solution right here. And the idea is, what is this right here? Well, if you write it up as y equals maybe 1/2 x squared plus c, you can actually see that this is actually a representation for a family of parabolas. Okay, so I'm going to say family. We are family. Boo-doo-doo-doo of parabolas, don't you see? All right, so why is it a family of parabolas? Don't you see? Come on, that was funny. If you just graph y equals 1/2 x squared, okay, that would actually be a parabola that's actually a little bit wider than y equals x squared. Don't worry so much about the horizontal stretching here. But if you actually make that c, equal to 0, then it's going to look like this guy right here. If c is equal to 1, you're going to shift it up by 1. If c is negative 1, you're going to shift it down by 1. Maybe c is positive 2. Maybe c is positive 3.5. Okay, maybe, c is negative 3. Negative 2. You can see you're really generating an infinite number of parabolas. So that's what this general solution represents, an infinite number of parabolas. That's a family of parabolas. Kind of looks a little bit like a menorah. So you can't actually find out what the real solution is unless they give you information to solve for c. And that won't be happening until we get down to example 3 over here. Okay, so that's the deal with the differential equation. Let's jump to example 2. All right, so we always want to separate before we integrate. Usually the first step to separating is cross multiplying. Always put dy on the left-hand side. So we get dy times 1 is dy, and then negative y squared times dx is negative y squared dx. And we've cross multiplied here, but we haven't separated the variables, okay? There's a y squared over here. He should be on the left-hand side with the dy. He shouldn't be with the dx. And, Mr. Berto's tips and tricks, besides putting the dy on the left-hand side, and after you integrating, putting only the plus c on the right-hand side, you want to keep the left-hand side as clean as possible. Don't bring any things over there that don't need to be there. What I'm saying is that this negative does not need to be moved to the left-hand side, okay? Keep the left-hand side as clean as possible. I might have said keep the right-hand side as clean as possible a moment ago. Hopefully I didn't, okay? It's the left-hand side you want to keep as clean as possible. So only bring the y squared over there, okay? And obviously you could divide by y squared on both sides, but that's the same thing as multiplying by 1 over y squared on both sides. So we multiply by 1 over y squared on both sides. We end up with 1 over y squared dy is equal to negative dx. So I just divided by y squared on both sides, essentially. And now you're separated, but you might not really be in the form to integrate yet. Maybe you want to write 1 over y squared as y to the negative 2 with respect to y equal to negative dx. And now we're actually set up in a situation where we can integrate. Okay, so let's integrate both sides. Okay, if you integrate y to the negative 2, add 1 to the exponent, divide by that number. Don't put the plus c, okay? We're just going to move him to the right-hand side. You're never going to have to worry about that plus c on the left. Integrate negative 1 with respect to x. That'd be negative x plus c. Okay, and now we just want to solve for y, and here's where things kind of get interesting, okay? I want to solve for y on the left-hand side. I want to get rid of those constants, okay? So I'll multiply my negative 1 on both sides. Okay, and the reason we do that here is that the negative ones are going to cancel out. You could have y to the negative 1, which, by the way, is 1 over y. Hopefully that's not too quick for you. Distributing over here is really cool because negative 1 times negative x is going to be x. But now we do negative 1 times c. Some people put negative c, but it's not necessary because negative 1 is a constant, c is a constant, and a constant times a constant is just another constant. So we're just going to put a plus c right there because negative 1 times c is just another c. You don't need to do that. You could put minus c, but I'm telling you, stuff like that is going to get really crunchy. This is the better way to do it. When you combine constants, you're just going to get another constant. We want to solve for y. A great little technique here is to actually reciprocate both sides. Okay, so 1 over y, the reciprocal is y over 1, which is just y. And here we get 1 over the quantity x plus c. And that right there is going to be my general solution. Sir! Okay, this is really a family of rational functions, believe it or not, okay? And depending on what c is equal to, it's going to change where that vertical asymptote is. You're not really supposed to know that quite as much as you might know that this one over here was a family of parabolas, okay? So solving differential equations, first separate, which usually means you start by cross multiplying, okay? Always put the dy on the left-hand side. Keep the left-hand side as clean as possible. Don't bring stuff over there that doesn't need to be over there, like that negative. It's going to mess things up, okay? You could actually end up with different general solutions that don't look exactly the same as mine over here, but essentially they represent the same thing. But that could really get confusing, okay? After you separate the variables, integrate. Make sure you only worry about that plus c on the right-hand side. Normally, we solve for y next, okay? But if you actually look at example 3, which I'm going to do on a piece of paper here because I'm probably going to run out of room. You can't see anything right now. There we go. Okay, I'll even write that dy over dx is equal to, what do we got, 4x over y. You can see that's a function of x and y this particular time. Then they tell you y of 0 is equal to 5. A nish condish, anybody? They're telling you the point 0, 5 lies on the original function. Hence, we'll actually be able to solve for y in this case, turning a general solution into a particular solution, okay? And we'll talk about that. And they want an equation for y in terms of x. You know, technically, you don't, when you get these general solutions or particular solutions, you don't always need to necessarily solve for y, but usually they're going to ask you to solve for y, okay? So that's something you're going to have to obviously worry about. So anyway, if you take a look down here, you know, what do we do first? Let's separate, then integrate, don't differentiate. Get it straight. Sorry, I'm having a lot of fun here. So, you know, if we cross multiply here, always put the dy on the left-hand side. Follow Mr. Berto's tips and tricks. Y times dy is going to be y dy. Y dy? Well, because y times dy is y dy. All right, terrible joke once again. Dx times 4x is going to be 4x dx. And the cool thing here is that after you cross multiply, you're already separated. So sometimes things work out, and they do here. You don't need to move anything. Some people are like, I want to bring the 4 over here, multiply by 1/4 on both sides. You could do that, but I'd suggest keeping the left-hand side as clean as possible, okay? Trust me, I got a pretty good method for solving these equations right here. It's been honed over many years. It's helpful, but there are many different ways to do these problems. We'll talk about an alternate way to do this problem as well. Anyway, if we integrate both sides, okay, here, y to the first, integral of y to the first is y squared over 2. Equal to, pull the 4 to the side, integrate x to the first, x squared over 2 plus c. Only need that c on the right-hand side. And thus this gives me y squared over 2 is equal to 2x squared plus c. And here's another Mr. Berto's tip and trick. You know, before I solve for y, I usually end up solving for what c is equal to. Because when you start using advanced algebraic techniques, when you're dealing with a c over here, because, you know, a constant, you know, times another constant, just another constant, that can get confusing for some people. So I would do this. On the left-hand side, after you integrate, I'd get rid of constants if you can. Like, this is simple to get rid of this 2 down here. Just multiply by 2 on both sides. You know, and here we'll end up with y squared is equal to 4x squared plus 2 times c. Just could be another c, just could be another constant. You know, right now, if you wanted to solve for y, you would have to take the square root of both sides, but you need to be careful with that, okay? You could take either a positive square root or a negative square root. It really depends on the particular solution, which one you would take. And sometimes people start breaking up square roots over addition, which we know is ridiculous. So my suggestion is the second you have to use an advanced algebraic technique to solve for y, I'm talking about square rooting. Maybe making both sides the argument of ln, okay, even reciprocating both sides, stuff like that. I don't really solve for y until I solve for c, People are like, how the heck are we going to solve for c? Well, we know that y of 0 is equal to 5, which just means the point 0, 5 lies on the original function. So I know when y is equal to 5, x is equal to 0. So I could plug that in. And you could do that before you solve for y. A lot of times it's easier to solve for c before you solve for y. Trust me. So replace the x with a 0. Okay, and here you can see we have 25 is equal to c. Now, depending on what your general solution looks like, you might generate different c's to go with it. So make sure whatever general solution you use to generate this particular value of c, make sure you actually plug that back into that general solution. So y squared equals 4x squared plus 25. Now it's a lot easier to solve for y because I have a number over here. I don't just have some arbitrary constant. And now when you square root both sides, a lot of people are like, wait, do we take the positive square root or the negative square root? Well, the information is right here, okay? You can see that our y value is a positive number. We know that 5 is positive. And we know that if you're going to take a square root and end up with a positive number, it needs to be a positive square root. You could check it right now. Replace the x with a 0. 4 times 0 squared is 0, plus 25 is 25. The principal square root of 25 would be equal to 5. It works. If you put a negative in here, you'd get y equal to negative 5 when x is equal to 0. So that would actually be incorrect, okay? So what you need to do is you just need to remember when you solve for y, and right here, by the way, we don't have a c anymore, so this is not a general solution. It's a particular solution. That's what we call that. And you want it in y equals form. It specifically said here, solve for y, okay, in terms of x. You can see that over there. Okay, solve for y. So I solve for y. So here's my particular solution. If you're a little confused, you're like, hey, how do I know if it's right? Take that initial condition, plug it in, okay? And if you plug in x equals 0, you get y equals 5 back. If this was a negative 5, then you want to actually put a negative in front. Okay, and there are different ways to do these, okay? I don't usually talk about this, but, why not? Because we have a video here. If you actually start here, so here's my general solution, right? I had y squared is equal to 4x squared plus 6. You could solve for y right now and actually square root both sides. You do need to have the wherewithal. What I put plus 6, that's supposed to be plus c. Good going, Berto. You do need to have the wherewithal to realize, oh, you know what? Y is a positive number. Thus, I want to take the positive square root. And you could stop there if you want and say that that's my general solution. And now we know that point 0, 5, plugging in, y is 5. Right, little square root action, 4 times 0 squared plus c. So here we'll actually get 5 is equal to radical c. And now if you square both sides, you get 25 equals c. So you actually end up with the same value of c that we did last problem. That's not always going to happen, okay? Because now we have to take this general solution that we used to generate this particular value of c, plug it in there, and now you can see we're done, okay? And we have the same answer that we had before. But sometimes things are going to happen, okay, to cause you to change that value of c right there to get it to match up with this particular solution. So basically what I'm trying to say is that if you use different general solutions, you might get a different c. Didn't happen here, but you might get a different c. But you will still end up with the same particular solution. Sometimes people end up with particular solutions that don't look alike, but they're actually algebraically equivalent. I think if you're smart, nothing wrong with wiping out constants on the left-hand side. Anything simple, addition, multiplication, subtraction, division, you could do that to move constants. But I don't use any advanced algebraic technique to solve for y until I solve for c first. And you'll see that'll become more important in different problems, okay? Essentially that's really the lesson for today. In your homework ditto, if you look at it, you're supposed to do number 4 and number 5 on your homework ditto. We'll do number 5 together, okay? You don't have to watch this if you don't want to, if the videos are going over too much for you. But, if you want to pause it right now, try number 5. And then when you hit play, we'll be right back here, okay? And maybe you want to try it right here. This is straight up from an AP. Sometimes you really got to worry about solving for y, and it can get really complicated. Your AP will be all free response. So really, it's only when you solve for y and you have to change things around in a multiple choice situation that can be difficult to match up your answers. But your AP won't have any multiple choice. It's going to be crazy the way they're going to do it, 45 minutes. Once again, it's still up in air about that, though, so let's not talk about that. But here's an AP problem. Consider this differential equation. Okay, I just considered it. And they want you to find y equals f of x, the particular solution, to the differential equation that passes through 1, 0. Anybody else smell an initial condition? Initial condition. I smell it. Anyway, so here, let's solve this differential equation. Remember that first step. Let's always cross multiply. And don't forget Mr. Berto's tips and tricks. Put the dy on the left-hand side. dy times 1 is going to be dy. And now over here, we end up with e to the y times the quantity. 3x squared minus what you want to grow it to be, success, dx. And look, you cross multiplied, but you haven't separated variables, okay? This e to the y is not supposed to be over there with the dx. This quantity is. So let's divide by e to the y on both sides. Same thing as multiplying by 1 over e to the y on both sides. I do that here for a particular reason. You'll see in tomorrow's lesson when we deal with an ln in a differential equation. Makes it easier if you do something like this. But look, the real reason we multiply by 1 over e to the y is if you just divide by e to the y, you get dy over e to the y. Some people get confused with that dy. Remember, you're always going to pull it to the side when you integrate anyway. So now you might not be in integratable form yet. You might want to write this as e to the negative y dy equals the quantity 3x squared minus 6x with respect to x. So now we have variables separated. We did right here, actually, in this step, we had separation of variables, which I'll give you points for on the AP. But now maybe you want to set it up this way so we can integrate. Don't hate, integrate. Okay, and if you integrate e to the negative y, this is where things get a little crunchy because you could use u substitution and set u equal to negative y. But in a differential equation, when you use u substitution, there's going to be more going on, and that could definitely get confusing if you have to do it on both sides. This is where mental integration really shines. Like, if you integrate e to the negative y, you're going to get e to the negative y back. Remember, don't forget about plus c. We only worry about that on the right-hand side. But remember, u substitution, kind of like chain rule for integrals. Just remember, chain rule, you multiply by the derivative of the inside. And integration, you divide by the derivative of the inside. The derivative of negative y with respect to y would be negative 1. So I'm going to divide by negative 1. Remember, e raised to a linear is one of the easiest mental integration situations. It's really up to you there. Integrate 3x squared. Pull that 3 to the side. Integrate x squared, which is x cubed over 3, minus 6 times the integral of x to the first. So x squared over 2. And there you got to put that plus c. So what do we get now? We get negative e to the negative y. And they want to see that integrating, by the way. You get points for that as well. Equals x cubed minus, 3x squared plus c. And you'll better have that plus c there. If you forget that, people are going to think you can just solve for y and be done, okay? But really, we need that initial condition, okay, to be able to solve for c. So don't leave that c out. Now look. Remember, I'm not going to solve for y before I solve for c, but you could do something cute right now. You could get rid of this constant, okay? After you integrate, you want to clean up the left-hand side. Always leave the left-hand side as clean as possible. So I'll multiply by negative 1 on the left and on the right. Okay, and that's going to give me e to the negative y is equal to negative x cubed plus 3x squared. Plus c. Remember, negative 1 times c is just another c. You could use a negative c there. You could try it that way. It still works, but it starts to get a little bit crunchy. Then I'll move this up here. Right now, this, by the way, is a great general solution, okay? Because right now, if you wanted to solve for y, you'd have to cancel out that e. You'd have to take the ln of both sides, make both sides an argument of ln. That's an advanced algebraic technique. You don't want to do that when there's just some arbitrary constant around. I don't solve for y until I solve for c first. You might want to write e to the negative y as 1 over e to the y. It's really up to you. Equals negative x cubed plus 3x squared plus c. And that's going to be my general solution. Sir! I don't know, 1 comma 0 is my initial condition. So now I plug in, just don't flub up plugging in y and x. I know y is 0, so 1 over e to the 0 is equal to x is 1, so negative 1 cubed plus 3 times 1 squared plus c. E to the 0 is 1, so 1 over 1 is equal to 1, equal to negative 1 plus 3 plus c. So that gives us 1 equals 2 plus c. Subtract 2 from both sides. Negative 1 equals c. So there's the c that I got that happened to go with this general solution. If you use the general solution, if you leave the negative over here, remember, remove that negative, you might end up with a positive 1 for c instead. Okay, there are different things. Just remember, whatever you use to generate the value of c, whatever general solution, take that and plug the value of c back into it. So now I get 1 over e to the y is equal to negative x cubed plus 3x squared minus 1. And now I can actually solve, okay, for y. bunch of different ways to do it. I mean, right now, it might be silly that I wrote it as 1 over e to the y, because if I left it as e to the negative y, I could ln both sides right away. But here, if you want, you could reciprocate both sides. The reciprocal of 1 over e to the y is e to the y over 1, which is just e to the y, equal to 1 over, I'll write this as 3x squared minus x cubed minus 1, just to make it a little bit prettier, okay? And now, you know, we could just make both sides an argument of ln, okay? See if we actually have the room for this here. Okay, hopefully I can get room. Oh, whatever. Okay, so over here, when I take the ln of both sides, I get ln of e to the y is equal to the ln of this whole 1 over 3x squared minus x cubed minus 1. And that means that y is equal to ln of 1 over the quantity 3x squared minus x cubed minus 1 right there. Okay, so that right there is the solution. Check my work, make sure I didn't make any mistakes. It's looking pretty good to me right there. You could circle it, okay, or box it in. That right there is definitely a particular solution. If it's a free response, you can write down whatever you want, okay? Also, if you wanted to, you can actually break this up and make it ln of 1 minus ln of the quantity 3x squared minus x cubed minus 1. Remember, log of two arguments, you know, if the argument has division, you could break it into two separate logarithms if you end up subtracting them, okay? And here, ln1 is 0, so 0 minus this thing over here would just be negative ln of 3x squared minus x cubed minus 1. And you have the solution to this in your ditto as well. Okay, so either of these would be acceptable. A part 1, you might need to worry about manipulating. You won't have a part 1 on your AP. Okay, so either of these would be fine. You can get to this one quite easily, by the way, if you start right over here with that general solution, actually ln both sides there. Okay, so a lot of different ways to do these problems. Hopefully that video wasn't too long. I'm going to try to stick them to 20 to 25 minutes. I could see them at 27 over here. So I'll do the best I can to tone it down, but we do have an AP exam coming up. Want to make sure you guys know what's going on. Okay, once again, most important thing is that everybody is home and safe and healthy. Okay, so my thoughts and prayers go out to your families. If you have any questions on anything, I've never done this before, okay? I can make a silly mistake. You might be like, I'm not understanding anything. What the heck is going on here, Berto? Email me, okay? Talk to me about it. Make sure you join that Remind, because at some point we're going to have to, you know, grade things. Yeah, I wouldn't worry about that right now. Please don't worry about that. I'll take care of you the best I can. But to submit assignments, the best way to do it might be to use Remind. Anyway, this is Berto signing off, and you'll have another lesson tomorrow. Once again, you know, get in touch with me if you need to. And it's a learning process for everybody. At some point, we'll be done with this. But right now, something we got to deal with. So everybody have a good day, and adios, y'all.